Honorable Vice Rector, Honorable Dean of the Faculty, Honorable Chairman of the Department, esteemed colleagues, dear ladies and gentlemen. I would like to present to you the scientific achievements and the personality of Professor Gerhard Weikum. It is my honor and privilege to do this today. I'll start with his career. I will repeat a few of the things that Professor Papaioannou presented. So his PhD was in the Department of Informatics in the Technical University of Darmstadt. Then he was the postdoc at MCC in the USA, then an assistant professor at ETH Zurich, then a full professor at Saarland University, and until recently, a scientific director of the Max Planck Institute for Informatics and professor of Saarland University. As Professor Papaioannou also said, he has received many awards for his overall contributions to computer science. He's a fellow of the German Computer Society, and he also has a very sought-after fellowship, probably the most sought-after fellowship in computer science, the ACM Fellowship, the Fellowship of the Association of the Computing Machinery. Another important achievement of Professor Weikum is the number of times that he has received Test of Time awards. These are awards that are given for publications in a specific year, in a specific conference, that are deemed to be the most influential in the next typically 10 years. So this is very important in terms of scientific contributions, and it shows the impact of Gerhard's work. And it is interesting to see that these contributions are in all research areas, all broad research areas to which he has contributed and about which I will talk now. So the first broad area of research where Professor Weikum has contributed is databases. And he has contributed to all the components of a database system. The storage structures, the indexing structures, query optimization, concurrency control, transaction management, everything. And he has written a well-cited book on transactional information systems. Additionally, he has also worked on databases for more expressive data models like XML and RDF. Another avenue of contributions by Professor Weikum is the area of information retrieval and web mining. Here, the data model is text, and Professor Weikum has contributed to text analysis, search engines, social networks and online communities, recommender systems, combining text with other modalities like images, and most importantly, fairness. Fairness is a very important issue these days, especially with respect to artificial intelligence. Finally, another dimension of research of Professor Weikum is the area of knowledge graphs, where he has contributed the knowledge graph YAGO, and also important ideas in knowledge harvesting, knowledge graph construction and curation, question answering, common sense knowledge, combining knowledge graphs with other sources of information, and most recently on combining knowledge graphs with large language models like ChatGPT and other systems. The work of Professor Weikum has significant impact. I will give you only one example, although I could give many. If you go today to Google and type, "What is the largest city in Crete?" you will get Heraklion, where I come from, but this is not what it is important about it. What it is important about it is that you get an answer. In the old days, when search engines became first available and we were using them, you would get links to web pages, and then you would click, read the text, and find out which is the largest city in Crete. With work in knowledge graphs, like the prominent work of Professor Weikum on the knowledge graph Yago, now search engines can return answers instead of links. The work of Professor Weikum has been recognized extensively by his peers. If you go to Google Scholar, you will see close to 45,000 citations and an H-index of 100. These are very big numbers for computer science researchers. Also, Professor Weikum has made a great contribution to the careers of young researchers. He has supervised very many PhD dissertations, and most importantly, his PhD alumni are now members in top universities like the Technical University of Munich, University California San Diego, other European universities, top universities in India, and so on. And also in very big industries like Amazon and Google and Microsoft and Bosch and so on. Professor Weikum has many scientific qualities. I know him for quite a few years, and what I have always admired in him is that he's an original thinker and a visionary. And he's pushing for impactful research. He's a talented team builder and team player, and you can see this from his group, which has been an inclusive and truly international group, and from his many international collaborations. He is always available to his students and would give comments to a submission to a conference even within a day. He's always managing to get the best out of his students. And in that way, he's a great supervisor. He knows the progress of every student, including interns in his group, at every point in time. And he's finally hardworking and focused on results. His motto is that what follows a paper is preparation for the next paper. And allow me to conclude by saying a few things about his personality. Professor Weikum is always smiling. He's very approachable. He's very friendly. He's happy to discuss things beyond computer science, because there is certainly life beyond computer science. He's a socially responsible individual. You will understand this if you talk to him. And he has a great sense of humor. Gerhard, it's an honor to have you here today. Thank you very much.
Αναγόρευση του τιμωμένου. Ανάγνωση των κειμένων του ψηφίσματος του Τμήματος της Αναγόρευσης και του Διπλώματος από τον Πρόεδρο του Τμήματος Πληροφορικής και Τηλεπικοινωνιών, καθηγητή κ. Δημήτριο Γουνόπουλο.
It's a great honor to do the oral proclamation, and it's an obligation to do it in ancient Greek. So, bear with me. So, Εθνικό και Καποδιστριακό Πανεπιστήμιο Αθηνών. Ψήφισμα του Τμήματος Πληροφορικής και Τηλεπικοινωνιών των Θετικών Επιστημών Σχολής. Τύχη αγαθή. Πριτανεύοντος εν το Αθήνης Εθνικό και Καποδιστριακό Πανεπιστήμιο Μελετίου Αθανασίου Δημοπούλου, κοσμητεύοντος εν το Θετικών Επιστημών Σχολή Ιωάννου Εμμανουήλ και προεδρεύοντος εν το Τμήματι Πληροφορικής και Τηλεπικοινωνιών Δημήτριου Γουνόπουλου, έδοξεν ομοφόνος το τμήματι. Gerhard Weikum, άντρα έφτε επεφικότα και παιδείας έμπλεων, εκ Γερμανίας ορμόμενων, εν το περιονίμου Ινστιτούτο Max Planck, τας περί τας βάσεις δεδομένων, τον παγκόσμιο ιστό, τα συστήματα συναλλαγών, την ανάκτηση της πληροφορίας και την τεχνητή καλούμενη νοημοσύνη, σπουδάς μ' άλλα προάγοντα και αρτιούντα, πολλές και καινοτόμους ερεύνας και συγγραφές εν τις ομοτέχνες διαλάμποντα και πλήθη φοιτητών διδάσκοντα, έγλη ζηλωτήν ανά τον κόσμο κτισάμενων και κατεξοχετέρων τιμηθέντα, προς δε τούτης την προς την Ελλάδα και τους Έλληνας εύνοια αυτού πολλαχή επιδεικνύμενων, επένεσε τε αυτόν και επίτιμον διδάκτορα του τμήματος αναδείξε. Το δε ψήφισμα τόδε με εμβράδυ αναγράψε και τον του τμήματος πρόεδρον δημοσία εν τη εθούση τη μεγάλη ανάγνοντα και τα στιμάς ανυπώντα επιδούνται αυτό ή αν ημέρα η αναγόρευσης γένεται καθά νενόμεστε. Εγένετο Αθήνηση μηνός Ιουλίου Τρίτη, έτους Τρίτου και 20ου και δεσχιλιοστού από Χριστού Γεννήσεως. Ο πρόεδρος του Τμήματος Πληροφορικής και Τηλεπικοινωνιών Δημήτριος Γουνόπουλος. Αναγόρευσης. Επειδή περ το Τμήμα Πληροφορικής και Τηλεπικοινωνιών των Θετικών Επιστημών Σχολής του Αθήνης Εθνικού και Καποδιστριακού Πανεπιστημίου, τον Gerhard Weikum, άξιον απίφυνε το επίτιμου διδακτορικού αξιώματος, η δε των Θετικών Επιστημών Σχολή τούτα παιδέξατο και ο πρίτανης την σχολής γνώμη επινεύει, διατάφτα εγώ, ο Δημήτριος Γουνόπουλος, καθηγητής των προηγμένων τεχνολογικών πληροφοριών, νυν δε του Τμήματος Πληροφορικής και Τηλεπικοινωνιών πρόεδρος, χρώμενος στη δυνάμει ειν παρά των πανεπιστημιακών νόμων και του Τμήματος έχω λαβών, Gerhard Weikum, επίτιμον διδάκτορα του Τμήματος Πληροφορικής και Τηλεπικοινωνιών των Θετικών Επιστημών Σχολής του Αθήνης Εθνικού και Καποδιστριακού Πανεπιστημίου, δημοσία αναγορεύω και πάσα σε αυτό τας προνομίες τα στον πανεπιστημιακό τούτο αξιώματι παραπεμόμενας απονέμω. Εγένετο Αθήνηση μηνός Ιανουαρίου 12η, έτους Τετάρτου και 20ου και δεσχιλιοστού από Χριστού Γεννήσεως. Ο πρόεδρος του Τμήματος Πληροφορικής και Τηλεπικοινωνιών, Δημήτριος Γουνόπουλος. Ελληνική Δημοκρατία. Πριτανεύοντος εν το Αθήνηση Εθνικό και Καποδιστριακό Πανεπιστημίο Γερασίμου Σιάσου, καθηγητού της Καρδιολογίας Μοριακής Καρδιολογίας, κοσμητεύοντος εν το Θετικών Επιστημών Σχολή Ιωάννου Εμμανουήλ καθηγητού της Άλγεβρας και προεδρεύοντος εν το Τμήματι Πληροφορικής και Τηλεπικοινωνιών Δημητρίου Γουνόπουλου, καθηγητού των προηγμένων τεχνολογιών πληροφοριών, Gerhard Weikum, αποδόγματος ομοθήμου της των Θετικών Επιστημών Σχολής, εις τους επίτιμους διδάκτορας εγκρίνομεν, μηνός Ιανουαρίου 12, έτους 4ου και 20ου και δυσχυλιοστού από Χριστού γεννήσεως. Ο πρίτανης Γεράσιμος Σιάσος, ο κοσμήτωρ Ιωάννης Εμμανουήλ, ο πρόεδρος του Τμήματος Πληροφορικής και Τηλεπικοινωνιών Δημήτριος Γουνόπουλος.
Περιένδυση του τιμωμένου με την τίβαινο της Σχολής από τον κοσμήτωρα της Σχολής Θετικών Επιστημών του Πανεπιστημίου Αθηνών καθηγητή, κύριο Ιωάννη Εμμανουήλ.
Ομιλία του τιμωμένου καθηγητή, κυρίου Gerhard Weikum, με τίτλο Adventures in Data, Knowledge and Language.
Dear Madam Vice Rector, dear Dean, dear Chairman, dear professors, dear colleagues, dear ladies and gentlemen, this is a terrific honor and pleasure, and thanks a lot, Manolis, for your most kind words in the laudation. It's receiving this honorary doctor from such a prestigious university is a huge honor that really means a lot to me. So I'm deeply moved, I'm most thankful. In this lecture, I'd like to sketch the long path in my career that led me through different research areas within computer science, hence the title Adventures in Data, Knowledge, and Language. But before I start this, a short digression. Of course, I have been curious about previous recipients of an honorary doctorate here at the University of Athens. I did my homework, and when I identified these four giants in their respective fields, I felt even more honored, more proud, but also, I have to say, a bit intimidated. It happens, though, I have personal relationships with each of these four. It's me to them, not the other way around, with one exception. The first, namely John Milopoulos. He was president of the VLDB Endowment, the organization that runs the VLDB conference series in the 2000s, and I became his successor as VLDB president. My relationship with Christos Papadimitriou will become clear on the next slide. Frank-Walter Steinmeier, honorary doctor of the law department, is, of course, the president of Germany. No further explanation needed here. And then finally, Mikis Theodorakis, who, of course, I've never met, but I've been a great admirer of him for many years, admiring his beautiful music, but also the political messages sometimes conveyed through music. So now let's get to the main topic. I started around 1980 when I was an undergraduate student. I liked theory, I liked compiler construction, and I loved this so-called Dragon book by Eho and Ullmann. Together with my friend Tobias Nipko, we wrote a master's thesis on ternary write system, motivated by compiler construction issues. And one of the results, we were lucky and it got published. This is our very first academic paper in this conference in 1983. Now what matters is not really this paper, it's totally irrelevant today, but the next paper, because right after our paper there was Christos Papadimitriou. So think about this, our names, two completely unknown undergraduates next to the name of the star in computer science theory. Christos also gave a keynote at this very conference, and I didn't know at that time, was about concurrency control, and that turned out to be a source of inspiration later on. For my PhD, I actually moved to a different area, namely database systems, again falling in love with another Ullmann book, which motivated me, and in '86, here you see me with my advisor Hans Scheck, I graduated, but I stayed in the database field for another 15 years or so. I worked on genuine systems issues, performance optimization, high availability, scalable architectures, self-optimization, these kinds of topics, and also concurrency control. In 2001, my co-author Gottfried Vossen and I, and you also see our editor Jim Gray, we finalized this 900 pages book that Manolis mentioned about transactional concurrency control and recovery. And then I said to myself, enough databases for the rest of my life, and I decided to leave this area of database systems. I became interested in search engines and web content, and in 2003, when I joined the Max Planck Society and also had certain resources at my disposal, the idea came up, maybe we can bring database assets to web contents. Specifically, can we apply structured queries, like in a database query language, directly to raw and noisy web contents, so that we would get precise and concise answers to questions like the ones shown here. Which science fiction books formed the basis of movies? Which basketball player scored the most points across all Olympics? Which alumni of our institute, MPI, won an ERC grant? These kinds of queries are completely easy to formulate and answer if all the relevant data were already in a single well-curated database. But that's exactly wishful thinking. In reality, the relevant information, the bits and pieces that give you the cues for answering these questions are spread across many web pages. They take different formats embedded in natural language text, in tables, lists, and all kinds of other formats. So we worked on this challenge for a number of years, combining database and information retrieval principles and methodologies. We were relatively successful, but we didn't reach the big breakthrough. So at this point, we reconsidered our goal and strategy and then redefined it, namely to aim at an intermediate stage. So the idea was first identify the absolutely crucial cornerstones of information within noisy web content, and these are the entities and the relationships that hold between them. And then we pull these out and organize them in some high quality knowledge collection, and this knowledge collection would then serve as a catalyst to drive the actual search process. And this started our strategic vision and mission to build large knowledge bases from web content at scale and with near human quality. And the vision became reality. This is another example of how search engines utilize knowledge bases today. I can type this keyword query, who wrote music for Mauthausen, and I get back this crisp, precise, concise entity answer, Mikis Theodorakis. This is actually one of his political pieces, Anti-Holocaust, which is a real masterpiece. Now, how is this made feasible? The search engine identifies words and phrases in my input and tries to map them onto entities and predicates of the back-end knowledge base. So here, wrote music would be mapped to a predicate composer, and Mauthausen would be mapped to this composition, the Ballad of Mauthausen. And then it's easy for the knowledge base to retrieve the respective object for such a subject-predicate-object triple, give it back to the search engine, and that can render a user-friendly result page. We can do this also with sets of entities. So the query Theodorakis records gives us this clickable panel of actual albums. So knowledge bases have found their impact in search engines and also in other kinds of big internet services, recommendations, for example, partly also in data analytics. But how could we actually get to this point, right? And where did it all start? And obviously this, although my group contributed, we were obviously not the only ones. So a minute on the history of what you might broadly call machine knowledge. Enhancing computers with general world knowledge has been a dream and goal in AI since the 50s. But it actually took until the 90s that real knowledge bases were constructed with notable content and size. Psych and WordNet were the two most notable seminal projects in that space. However, their content was completely handcrafted by knowledge engineers. So by that, they were inherently limited in scope and in scale. Then Wikipedia came along, and over a few years, it got also mature. It got rich in size, but also in content quality. And for the first time in the history of mankind, a substantial amount of human knowledge was in digital form in a single website. However, this content, all natural language textual articles, this was written by humans and it was intended for humans, for human reading. For computers and algorithms, this would be gibberish. But there was an opportunity, and that opportunity was seized by a number of projects, ours including, namely devise new algorithms that tap into this expressive content and distill out the most informative, the salient pieces of information and organize them into a formally represented knowledge base. Formally represented being important because we wanted to use this as a catalyst to drive other programmed applications, not just end-user applications. So these projects delivered proofs of concept already at scale, and they also developed important principles of the methodology, how to build and curate and maintain large knowledge bases. So this was quite influential, and a few years down the road, industry picked up many of these ideas. They built their own large knowledge graphs, as they prefer to call them, but they certainly built on the methodology that was laid out before. Today, the largest public knowledge base has 100 million entities and a few billion facts, but the industrial ones, especially on the back-end side of search engines, are 2 orders of magnitude larger. This is a bird's eye view of how a knowledge base can be constructed. Human knowledge has digital traces on the internet, structured data, but also unstructured content, especially natural language text, also images, videos, of course, but text is the main source. Think of books, scientific publications, news articles, and so on. And algorithmically, we can tap into this content and distill out, pinpoint and distill out the salient entities, that is people, places, products, events, and so on, and we enter them in a slowly growing, initially empty knowledge base, where we organize entities in a type or class hierarchy. So here we have Ennio Morricone, the Italian composer, we have a piece of music, and we have a movie. And other algorithms can often, not always, but often infer relationships. Like here, Morricone composed this piece of music and it was used in the movie. Now, once we have such a core of world knowledge, we can devise other algorithms for better coping and interpreting vague, noisy, and ambiguous natural language in web pages. And this way, we can acquire more knowledge, deeper knowledge, better knowledge at large scale. The methodology for doing this comprises a wide spectrum from patterns and rules, sometimes automatically induced from examples, to a wide variety of machine learning methods, all the way to constrained reasoning, logic-based constrained reasoning, which is important for consistency and for quality assurance. So let me now drill down a little on this technical machinery to give you a flavor for some of the contributions that we made. Suppose we want to populate this as one relation, which person has won which awards. We devised a method that we called knowledge harvesting that is based on distant supervision from a few seed facts that we would have in an initial core knowledge base, or we would manually construct these initial seed facts. For example, Björk won a Grammy and Jeff won the Turing Award. Now we can use these entity pairs to search in web contents or a large text corpus, find their occurrences within certain proximity, and then apply pattern mining algorithms to lift the observed texts into informative, frequently occurring patterns. And then the patterns can be used to search for new entity pairs, which give us fact candidates now. Here about Leo, Christos, and Yanis. We keep iterating, we get more patterns, but now also some questionable ones, obviously, that would not be good in for the actual knowledge harvesting. One more iteration, and now we get new fact candidates, but again, some are doubtful. Manolis, some Manolis. I'm using only first names for privacy reasons here. So he became the most valued player in the American Basketball League, and some Giannis won a Grammy Award. Now, obviously, this whole process is prone to picking up more and more noise. It gives you higher recall as well. We pick up more candidates, but there's also increasing noise and an increasing false positive rate. So we have to tame this somehow, counter, and we can use and have developed methods which use smarter statistics in the pattern mining algorithms, better ways of deep learning. But by and large, it's still the whole paradigm of knowledge harvesting is good for high recall, but it's not good enough by itself for high precision. So we need something else, and we did this additional stage as well. Second stage of knowledge-based construction is this knowledge curation. The idea here is that we use consistency constraints in order to jointly reason about the validity or non-validity of the fact candidates in such a pool of hypotheses, where Yanis, ACM Fellow, Manolis, European AI Fellow, Manolis also basketball champion, Yanis Grammy winner, and there are also fact candidates about class memberships, and some of these are also not necessarily valid in reality. Now we postulate consistency constraints, such as these. Obviously a toy example here. If you win a science award, you have to be a scientist. That kind of makes sense. If you win a sports award, you have to be an athlete. If you win a music award, like the Grammy, you have to be a proficient musician. But now we postulate also mutual exclusion between these three classes. If you're a scientist, you cannot be an athlete at the same time. So it's either brains or muscles, never both. And likewise with musicians and scientists and so on. Now we have these two sides, the fact candidates, noisy, and we have these postulated meta-level constraints, if you wish. We can put them together by plugging in the fact candidates from the left side into these logical formulas on the right-hand side. And this is a step known as grounding in computational logics. And this gives us a set of so-called clauses. These are simple formulas in propositional logics. No variables involved, no quantifiers, just plain simple formulas. Even though there's a formal notation here, you can still read them just from left to right. In a practical setting, we would actually get easily millions of clauses in order to work with, because we might have a huge pool of fact candidates, and that grounding process kind of increases the number of combinations as well. The constraints, by the way, they could be handcrafted by a competent knowledge engineer. It's not so much work, it's much less than it seems to be. Or they could be induced, that is learned from data in an unsupervised manner. Now, a large pool of clauses would almost always be inconsistent because of that noise from the ingestion process. But we can aim at computationally identifying a large subset that is consistent. And that would be the desired output, and this is the high quality, shown to be valid with high likelihood set of facts that we would enter into the knowledge base. Now this should, for the computer scientists in the room, this should ring a bell, because this is the MAXSAT problem, maximum satisfiability. It's the mother of all NP-hard problems, the very first problem that was shown to be NP-hard. NP-hard meaning that today's computers cannot solve them perfectly within reasonable time. More specifically, we're dealing here with a weighted MAXSAT problem, because the noisy fact candidates from the left side carry confidence weights that come from the previous harvesting process, and the constraints can actually be soft constraints tolerating exceptions to some degrees, to varying degrees, hence they also carry weights. We devised an approximation algorithm that is customized to the shape of the clauses that we deal with in our setting. There's a particular shape very frequently because many clauses are generated from mutual exclusion constraints. And our algorithm scales out onto distributed systems. Now, equipped with this machinery, we can revisit our fact candidates, scrutinize them, and clean out the false positives. So sorry, Manolis, no basketball championship, and Yanis, you have to give back your Grammy as well. So much for knowledge-based construction and curation. Now a few minutes on the backward direction. So if machines have this rich and algorithmically usable world knowledge, does that help in interpreting natural language? This focuses on this NLP task of so-called named entity disambiguation. Given an input, such as Leone used the Maestro's ecstasy theme in the dramatic graveyard scene, we need to identify mentions of entities. I did this already, Leone, Maestro, ecstasy, but we don't know who is Leone and who or what do we mean by Maestro and ecstasy. A knowledge base can enumerate candidates from its rich repository of entities, like Sierra Leone, the movie director Sergio Leone, Ennio Morricone, composer, conductor, also known as Maestro, the Maestro pay card, the methamphetamine drug ecstasy, or a piece of music, the ecstasy of gold. This gives us a combinatorial space of possible mappings from the mentions left to these candidate entities right. And even for such a small input, a realistic setting would have thousands of candidates on the right side. And one of these is correct, and the most natural and easiest way of computing this is to leverage contextual similarity between mentions on the left side, where each mention is surrounded by other text, and entities and their descriptions on the right side. Descriptions coming also from the knowledge base. This works in many cases, but not always. But humans actually can do better on such situations, and what they bring to work is their really rich world knowledge, general background knowledge, and their knowledge that a set of entities are likely to co-occur in a meaningful text only if there are certain relationships between them. And speaking of relationships, this is what the knowledge base can also help us with, Maybe the general world knowledge is not as comprehensive as that of a smart human, but it goes some way. We get cues from the knowledge base, like Sergio Leone directing this movie, the movie having a soundtrack which includes The Ecstasy of Gold, and that was composed by Ennio Morricone. So it's the combination of contextual similarity and that coherence of entity pairs or entity subsets that leads us to practical algorithms. This approach can be cast into different kinds of families of algorithms, including dense subgraph algorithms, which is what we advanced for this purpose. Our solution can handle named entities, but also co-references, for example, pronouns that appear in text, he, she, it, them, their, and so on. And also the semantics of common words. For example, the last word in the text seen is not an entity, but a common word, but it's also an ambiguous word that should be disambiguated. And our open source tool suite works with text tables, lists, combinations, and you can plug in your own knowledge base. So you can use Iago, our work, but you can also bring your own. What's next? What are the new frontiers? And these are three challenges that our group is currently working on. And an overarching theme here is to consider, of course, large language models like OpenAI and these kinds of models that are about to revolutionize the world. So what can their huge but latent knowledge bring to this theme of further expanding the scope and scale of knowledge bases? One of the challenges is knowledge about long-tail entities, such as Greek lyra players. Even the largest knowledge bases have only a handful or so of these instrumentalists. Language models generate more, but none generates any women or lists any women, which is kind of unlikely. And the language model also gives this questionable name, Vangelis, who is known for electronic music, but certainly not for lyra. Quantitative properties of entities that require a unit and proper context for interpretation is another open issue. When you consider as original motivation queries like women who ran a marathon under 2 hours 20 minutes, or which woman ran the most marathon under 2:20, you try to use knowledge bases for that. You find 600 female marathon runners, but only 10 or so have an actual time in the knowledge base. And language models don't work at all for whatever reason, and search engines don't give you this easily either. So it is an open issue. Last but not least, common sense knowledge about everyday objects and socio-cultural knowledge about human activities and behaviors. This would be a great asset for next generation AI to be more robust and more human aligned. For example, why is the cartoon with this cheetah funny? And what's the cultural context for the happy people in the photo on the right side? Wrapping up, I'd like to conclude by thanking the people who have a large share in all these achievements, above all my students, postdocs, one of them being in the room actually, or two actually, and other members of our team over many years. It's been a privilege to work with such bright and creative people. I'd like to express my thanks to my teachers and mentors at different career stages. I was always lucky with having great mentors, some also in the room, at least one, and collaborators also present here in a variety of contexts. I've learned a lot from each and every of these wonderful people. And the final slide is just visually highlighting 3 stages of my 40-year adventure in research. My alma mater, the Max Planck Institute, and the National and Kapodistrian University of Athens today. The common factor is pretty obvious. Athena has been a great companion throughout my professional life. Thank you very much, and thank you for bestowing this great honor on me. Thank you.
πέρας της εκδηλώσεως. Ευχαριστούμε πολύ για την παρουσία σας.